In this session, we will look at the basic operation of PLL. So, we will start. So, we are going to look at basic operation of phase lock loop. So, previously we have looked at PLL as a block which generates frequencies as we desire. Okay. So, here I will first draw the block diagram of a phase lock loop. So, you have a block called phase detector. It has two inputs and the output of the phase detector goes to a loop filter. This is loop filter, and output of the loop filter goes to a voltage controlled oscillator for now. The output of the voltage controlled oscillator comes back as a feedback to the phase detector. Okay. Here the input signal is V in, which feeds to PD, and the output of the PLL is V out. Okay. So, this whole is a block diagram of a PLL, you can say in general. Okay. Here PD stands for phase error detector. We will see what it does. Okay. Phase error detector. LF stands for loop filter, and VCO stands for voltage controlled oscillator. Okay. So, if this is a PLL, it should generate some periodic signal at the output, and this particular PLL has input also a periodic signal. So, here V in is actually a sinusoidal input, A in times sine of omega in times t, where omega in is the frequency of the input signal. V out is A out times sine or cosine, whichever signal you would like to write, omega out times t. Okay. So, we feed to this block PLL. Let me just put this as a one single block. Okay. We feed sinusoidal signal at the input V in, and we get a sinusoidal output V out. For now, we will restrict ourselves to sinusoidal signals at the input and the output. Okay. Now, based on the discussion which we had in the last session, this parameter omega in times t is nothing but the phase of the input signal. So, I can write phi in of t as omega in times t. Okay. And phi out of t is equal to omega out times t. Omega in is the input frequency, omega out is the output frequency. Okay. So, this block phase error detector somehow, we do not know how, but somehow for now phase error detector computes the error between the input and the output phase. So, I define a term called phase error. Phase error at any given instant of time is your input phase minus output phase. So, phase error detector computes the error between the input and the output phase, and it gives a voltage. The output of the phase error detector is voltage, not some other variable. So, it gives the voltage proportional to the phase error. So, you can say that the phase error detector output, which is error voltage, is proportional to the phase error. Now, this is interesting, as you can see that the input to the phase error detector, the two input signals are both voltages, right. They both are voltage waveform, both are sinusoidal. But the phase error detector operates not on the voltages here, but it operates on the phase error, and it gives the voltage which is proportional to the phase error. Okay. Now, this particular error voltage is filtered using a loop filter, and it gives you a control voltage V c. So, loop filter actually filters error voltage to give V c. Okay. This particular control voltage is used to control the frequency of the oscillator, frequency of the voltage controlled oscillator. So, what does the voltage controlled oscillator do? It actually, the output frequency omega out for the voltage controlled oscillator, omega out will come as in proportional to the control voltage. Okay. And when you change the frequency of the oscillator in proportion to the control voltage, you will actually change the phase at the output of the voltage controlled oscillator. Okay. So, we will look at it in in detail one by one. So, first one was phase error detector. So, as I said, phase error detector gives you it gives you voltage proportional to the phase error. So, you can think about it that the PD output V error is proportional to phase error. So, you can think about it, it may, because this is directly proportional, it can be a straight line characteristic between V error and phi error. Okay, this is V E here. So, it's like this. Okay. The straight line characteristics between the phase error and V error will be something like this. Okay. The slope of this particular curve is defined as a gain of P d, which you can define as K P d, and K P d is derivative of V error with respect to phase error. Okay. So, when you have a certain phase error at the input of the P d, you get an error voltage proportional to the phase error, and the gain of this particular phase error detector is K P d, which is defined as derivative of error voltage with respect to the phase error. The units of K P d, if you look from here, that will be your voltage with respect to radians, because phase is measured in terms of radians. So, once you get the P d output, which is a voltage in proportion to the phase error, you filter this, and when you filter this particular voltage with the loop filter using the transfer function, loop filter has a certain transfer function. So, I can write like this: loop filter transfer function LF of S, this is Vc of S by V error of S. Here S is signifying the Laplace transform. So, whatever voltage you get here at the input of the loop filter, you filter and you get the voltage. Now, you have the VCO. So, as I told, VCO output frequency is proportional to the control voltage. In general, your omega out frequency has two terms, which is omega free running frequency plus k VCO times your V control. Okay. So, every term has a meaning here. Your omega free is free running frequency of the oscillator. So, oscillator is a block which generates these sinusoidal outputs. So, omega free is free running frequency, k VCO is the gain of the oscillator. Okay. Now, if you would like to look at this in plot form, what you have here is, with respect to the control voltage, your omega out has characteristics like this. This you can say it is free running frequency, okay, omega free. The slope of this particular curve is k VCO. Okay. So, after knowing this, if you come back to this block, you see you have the input as a sinusoidal, output, the oscillator is a block which generates sinusoidal output, and if there is any error between the input phase and the output phase, the phase error detector generates the voltage, the error voltage at its output, which is proportional to the phase error. The error voltage gets filtered using a loop filter, generates another voltage. This particular voltage changes the frequency of the voltage controlled oscillator, and as you change the frequency of the oscillator, you change the phase of the oscillator. Okay. So, when you change the phase of the oscillator, your error voltage will actually reduce, and input phase and output phase, they will come closer. Okay. In this particular PLL block, what happens in a steady state, or you can say in locked state, when things have settled, following things will happen. That omega input and output frequency is going to be same. Omega in will be equal to omega out in steady state. Okay. And the rate of change of phase error with respect to time will be 0. Okay. This is the condition for the steady state, or you can call this as a locked state of PLL. Okay. So, we will take an example to understand a little more detail. So, given this block diagram, you give the input signal, you have a certain phase. So, I will just take an example here. Okay. So, as we know that we are operating on the input and the output phase, I will write only the phase variables as phi in and phi out. We know the actual signals are voltages, but the loop is operating only on the phase signals. So, if I am going to change the phase delta phi in, just an example, if I increase the phase or I applied any change at the input, I will get a change in the error voltage. This change in the error voltage will be reflected at the output of the loop filter as a control voltage. Okay. and this control voltage changes the frequency of the oscillator by delta omega, and the output phase is going to change by the integral of this change in the frequency. You will get a change in the output phase such that the change in the output phase actually delta phi in minus delta phi out, that will actually approach to 0. In a steady state, either this approaches to 0 or the rate of change of this phase error becomes 0. So, the phase error will not change with respect to time if the PLL is locked. Okay. Now, this is little interesting, that I have a block where my actual signals are voltages, but the different blocks in this PLL, they are operating or not on the voltage or current signals which we are used to learn in our system, but they are actually operating on different variables like phase or frequency, right. And it is not easy to extract the phase or frequency of the signal using different circuit elements which we know, okay, but we have to design in such a way that they operate on phase and frequency. Okay. Now, this, if you look at this particular block, the PLL block which we have seen, this seems to be operating in a similar manner as a voltage follower, or you have a buffer which operates. Okay. So, for example, you are used to see a simple voltage buffer. I will just show you like this. This is a regular voltage buffer which you have used, where you have the input voltage and you have an output voltage. Okay. So, this is a voltage buffer or a voltage follower. Okay. Just like a voltage buffer, you have this PLL block where you have the phase detector, loop filter and your VCO. Okay. And in this particular PLL block, it is not the voltage, output voltage which follows the input voltage, but it is the input phase which controls this block, and output phase follows the input phase. So, if you would like to draw the similarities between your voltage buffer and your PLL, here V out follows V in, okay, whereas in this case your output phase follows input phase. Okay. Why this is it is important to understand that this is similar, the phase and frequency which you are seeing in the PLL, these variables are similar to the voltage and current variables in the amplifiers and other blocks which you have learned and which you use now and then. Okay. So, in this case our variables in general are voltage and current. Here the input and output variables which we are interested in are phase and frequency. Okay. The way you have analyzed, or you would like to analyze this particular amplifier and the voltage buffer using transfer functions, right, using transfer functions like V out of S by V in of S. In a similar way, you will analyze the input and output phase using same kind of Laplace transform, Bode plots and others for transfer function like this. So, here the transfer function which we will be interested in is like phi out of S divided by phi in of S. Okay. In this case, so this is the similarity between your simple voltage buffer and your PLL block. Okay. Now, you may find little confusion that when we look at the transfer function H of S in voltage domain, right, there we see that okay, this H of S has a certain transfer function, it has frequency and phase information for the voltage transfer function. Now, we are talking about the transfer function for the phase phi out, which is actually a phase, and phi in, which is also phase. So, just to help you understand that when we talk in voltage domain, when we talk about the transfer function H of S, V out of S by V in of S, right. And for example, I will just pick up one low pass transfer function, let us say 1 plus S by omega p. It is a low pass transfer function with the pole at omega p, right. You can draw this transfer function like this, okay, where you have a pole, a frequency omega p. So, this is the transfer function which I plot, right. So, when you have this transfer function with respect to input voltage and output voltage, what does it mean? It means that if my input frequency is input signal is within the signal bandwidth of omega p, it will pass through. If I have signal outside the signal bandwidth omega p, it will actually get rejected. Okay. Or you can say, if you apply any change at the input which is within the bandwidth of this transfer function, that will be that will come at the output, whereas if you apply any input outside the bandwidth, that will be rejected by the filter. Similarly, if we take the transfer function for, so I think this is better. So, we have looked at the voltage transfer function in voltage domain. In the same way, if I look at in the phase domain or a PLL domain, same transfer function H PLL of S as phi out of S by phi in of S. This is 1 plus S by omega p, transfer function is same. Okay. So, here the transfer function which I am plotting is for input phase and output phase, not for input voltage and output voltage. This is something which you should be clear here. So, I have this PLL of S. If I apply any change in the input phase at frequency omega 1 lesser than the bandwidth of the filter omega p, I will see that change in the output phase. If I apply any any change in the input phase beyond the bandwidth of the filter, then that change will be rejected and I will not see, or I will see very attenuated attenuated frequency at omega 2 at the output of the PLL. Okay. So, please do not get confused between the frequency and phase of a transfer function with the frequency and phase used in the PLL block. In the PLL block, frequency and phase are the variables. Okay. You can have omega in and omega out also. Okay. So, this is where we have a similarity between the voltage domain and in the phase domain, and whatever analysis we learned for the voltage in the voltage domain circuits, the same analysis will apply in phase domain also.